Okay, start. So we're moving on to the next section, which is 1.6. Logarithms. How many of you have encountered this before? Okay, so a lot of you. So it's still a lot of review, but again, we're going to go over the basic rules, make sure that we are very well aware of them. Because when we move on to calculus, if you're not like super solid on the basics, it's going to catch you. So start out with a definition. The logarithm. A number to a given base is the power which the base must be raised to give the number. Right? That is the logarithm of a number is a power. The power of what? A certain base that you normally write down here. So this leads us to rule 1, which you can even take as a definition. I'm basically going to write what this sentence is saying in terms of math. So this is sort of like the definition of a logarithm. And it's a very useful definition. It says that the logarithm to a given base of a number is equal to the power. So basically that writing this kind of equation down is the same as writing this kind of equation down. And that's what I want to get. Okay. So the logarithm means that if I take this base, raise it to that power, I get this number. So for example, I can say log to the base 2 of 8 is 3. Because if I take 2 raised to the power 3, I get 8. Okay. So logarithm is kind of another way to write an exponential equation where it's the power that's the focus. You're really focusing on what the power is. So you're not focusing on the base, you're focusing on the power. It's just a change of perspective. But that change of perspective comes with a lot of nice things. For example, we realize that when you multiply things with the same base, what did you do to the powers? You added the powers, right? Or if you divided things of the same base, what did you do to the powers? Subtract the powers. If you take something that has a power and you raise to another power, what did you do?
Multiply.
You multiply the powers. So really, when things are happening in the base that are complicated, what's happening in the power is less complicated than what's happening in the base. Here you're dealing with multiplication. In the power, you're only dealing with addition. Here you're dealing with division, which is inherently rife with danger. And then this one, the powers are really only doing subtraction. Here when you're taking a base raising to a power, in the power you're only doing multiplication. So a log can turn multiplication into addition, it turns division into subtraction, it turns exponentiation into multiplication. It like brings all the operations down a notch when you sort of focus on what's going on up here as opposed to what's going on down there. Okay, so it's a really powerful technique for dealing with some really big numbers. You often take the log of certain numbers. That's why some of you guys in your science classes, you might do like log plots of something, like you're doing your chemistry labs, where instead of plotting x versus y, you plot log x versus log y, because the numbers are so huge, the logs actually break them down a notch and make them more manageable. So that's what a logarithm is. So it's basically this rule. It's a very important rule. It's basically going to be the definition. Okay, so that's rule 1. There are a bunch of rules that you need to know. I'm going to give you about 9 of them. The first 5 are very important. well, I'd say the first 4 are very important, but the remaining 5 you can kind of derive from the first 4, but it's good to know them by heart, because it'll make your life easier if you automatically know them by heart. But you have to know like the first 4. So that was rule 1, that's the definition, you have to know that. Rule 2 is like the guy was saying. If you have log to the base a of something being multiplied, you can actually change this into addition. So log to the base a of a product, you can actually break up the product and a log goes on each of them. Alright, so an example. If I have log to the base 3 of 2x, I can write this as log to the base 3 of 2 plus log to the base 3 of x. This is a valid simplification. Rule 3 is the one that talks about the division. So if I have log to the base a of x over y, a division happening, I can actually change that into a subtraction. So, example of that. If I have log to the base 7 of 2 over x, I could actually write that as log to the base 7 of 2 minus log to the base 7 of x. Okay, so I can go from a complicated expression to 2 simple expressions. Rule 4 is the exponentiation rule. Log to the base a of something to a power, I can bring that power down in front of the log. So, example, if I have log to the base 9 of x cubed, I can write that as 3 log to the base 9 of x. So those are rules you should really know. This is a very useful rule. I'll use it to derive some formulas later on, but it has uses in its own right. Most of the time you probably won't use it to simplify stuff, but I'll use it. So the first 4 rules, very important. This 5th rule is called the change of base formula. It's a rule that allows you to change the base on a logarithm if for some reason that base is not convenient for you to work with. It says that the log to the base a of b, you can write that as log to the base c of b divided by log to the base c of a. Right? Where c is some new base that you're introducing that's convenient for you to work with in the context you care about. I'll do an example. Let's say I have log to the base 4 of 8. What is that?
Log to the base 10 of 8 over log to the base 10 of 4.
To the base 10? Why would you use base 10?
Just because that's what's assumed in the calculator when you put log, isn't it?
Sure, but I'm not asking about a calculator. How would you do it on hand?
Well, it's 2. Or no.
So in other words, I'm asking what power do you have to raise 4 to in order to get 8? No, 4 to the 2 is 16. 4 to the half is radical 4, that's 2.
3 halves.
Right? At first, there are not many numbers to try here, but at first you might think, okay, if I raise 4 to the 1, I get 4. If I raise 4 to the 2, I get 16. 8 is obviously between 4 and 16, so it has to be a number between 1 and 2. Is it exactly in the middle between 1 and 2, or is it somewhere else? Like that you're probably not sure about. But what you can do is realize that it's weird. No one thinks of 8 in base 4. So, but in terms of 4 and 8, we actually know what those are in base 2. So in this case, rather than log 10, I would use log 2 as the convenient base. I would say this is log to the base 2 of 8 divided by log to the base 2 of 4. Now what is log to the base 2 of 8? 3. Because I need to raise the base 2 to the power 3 in order to get 8. What do I need to raise 2 to in order to get 4? 2. So it turns out that's the logarithm. It's 1.5. So 4 raised to the 3 over 2 power is going to give 8. And you can actually do that, right? When you have 4 to the 3 over 2, remember that actually means the radical of 4 cubed. Right? And that makes sense. Yes?
Is there a reason why B goes over C in the formula? Or is it just how they do it?
What do you mean B goes over C?
I mean, why it's B over A versus like A over B or something?
It's not A over B, it's a notation. It's a notational thing. It's kind of like when you have a radical of x. Sometimes they might put a little number down here to emphasize what base you want to work in. That's how this a functions. You don't think of it as b divided by a or b over a. This a here is identifying to you what base you're working on. Right? Same way that a little number here would identify what radical you're taking. Right? So that's how you want to think of these little numbers here. Don't think of it as like a division or something over something. It's a notational thing. Right? So this log to the base a is something by itself, and you're taking it of b, right? So you're thinking about something like f of b, where f is the log to the base a function. Right, so yes, that's important to know, because I do actually see students make that mistake sometimes. They think somehow there's a division implied here. It's not division implied. This is just telling you what the base is. So it's a notational thing, just like how you put little numbers on a square root, you can put little numbers on the bottom of a log. It's an emphasis for what base you're working on. So you could figure out what this is by changing the base to something convenient. By the way, remember last time we were dealing with exponentials. Remember, a log was just a different way to write an exponential, right? If you see this, remember it means this. Now this guy should remind you about a function like a to the x when you're plugging in the number c, right? And last time we spoke about functions like this, and we spoke about one that was very convenient for us in calculus, right? You guys remember what that was? E to the x, right? So it turns out if the exponential function e to the x is very convenient for calculus, then if we're going to do calculus with logs, log to the base e would be very convenient for us, right? This rule will allow us to change any random log into a log to the base e, because e is a nice thing to work with. And we'll see that later, but that's why this rule is important for us, right? Because really, there's an exponential background in here, and the base we might want to change at any random time. So we need to be able to do it in terms of a log as well as an exponential. So now rule 6, these are just some rules that I think it's really nice for you to know very quickly. But you can derive them very easily by knowing how logs work. So rule 6 I would say is log, you can put rules, from this point on you can put rules in quotations if you want, because these are just very specific things. So this says log to the base a of 1 equals 0. Log of 1 is always 0. It doesn't matter what the base is. Log to the base 2 of 1 is 0. Log to the base 3 of 1 is 0. Log to the base 17 of 1 is 0. Log to the base 15 million of 1 is 0. Log of 1 is always 0. Why? Because you take base a raised to the power 0, you will get 1. Any number that's non-zero that you raise to the power 0, you will get 1. So that's just something you can know very quickly. Anytime you see a log of 1, it's 0. Slightly related to this, what is log of 0? Right, so remember what this means, right? this should be a number that if I take a and raise it to that power, I will get 0. So let's say I have 2. What power can I raise 2 to in order to get 0? 2 to the what power gives me 0? There is no such power. Log of 0 is undefined. You cannot take the log of 0, right? If I give you a positive number, there is no power you can raise it to in order to get me 0. Because 0, it has to be 0 in the base, and the base is not 0. So log of 0 is undefined. Which I probably should emphasize that in our theory here, we're really assuming that a is greater than 1. Right? So it is a positive number that's bigger than 1. In the whole thing. And we never really worry about a less than. If our a is between 0 and 1, then we can kind of think of it as 1 over something, where this guy is bigger than. And base 0 doesn't make any sense because 0 raised to anything just gives you 0, so you'll never be able to solve anything, so it's no point looking at it. And if you pretend a is a negative number, you can always factor negative signs out and work with them separately. So the theory is basically built on things that are bigger than 1. It's the only important case that we really need to care about. So if I give you a number that's 1 or bigger than 1, you cannot raise it to any power to get 0. So log of 0 is always defined. You also cannot raise any base to a power to make it negative if it's positive. Right? So you'll notice that log of the domain of the logarithm is actually going to be greater than 0 as well. That's rule 7. Here's rule 8. Now this rule is pretty important, but it kind of falls into your lap though. Rule 8 says log to the base a of a to the x is, what power do you have to raise a to in order to get a to the x? X. Rule 9. This one is kind of the opposite of that one, but it's not as obvious to see why it's true. You have to work a little to prove it. It's not a long proof, it's maybe 2 or 3 steps, but it's still, I don't want to consider it here. I proved it in my other class if you want to watch the video for that in 1207. But the rule says the opposite of true. If you have the base and you plug the log into the power of that, it also gives you x. Now we're going to talk about some important notation. We said base e was very convenient for us, so we will use a special way to denote a log to the base e. Call it ln. Whenever you see this symbol, it means log to the base e of x. I'll never actually write log to the base e. Whenever this is what I mean, this is what I will write. Okay, so whenever you see this in your textbook, or on a quiz, or on a test, or on the board, it means that this is a logarithm and the base is actually e, but I'm not going to write. And if you just see log of x where no base is written, that implies that it's log to the base 10. And this applies to your textbook as well as your calculator if you have one. So on your calculator, when you put log, it will assume it's base 10, so it will work in base 10 when you're doing it on your calculator. If you type in ln on your calculator, it will assume it's base e, right? For any other base, your calculator actually does not work in any other base. If you want to work in another base in your calculator, use the change of base formula, right? So if you wanted to, in your calculator, to calculate something like log to the base 7 of 236, what you would do in your calculator is you could type log of 236 divided by log of 7. Just use the change of base formula. Okay, so your calculator can only do these 2 bases. And these are the only two bases that I will use without specifying, right? So if you see ln, it means the base is e. If you see log, it means the base is 10. Not going to care too much about this because, again, like I said, it's calculus. Base e is the most convenient base to work with. So ln is something that you're going to have to be aware of. Another thing you'd have to be aware of is note, it looks different, but it's a log just like any other log. E is a number that's greater than 1, it's 2.71828, blah, blah, blah. And so all the log rules that I mentioned before apply to ln of x, right? So for example, if I see ln of something times something, I can split that up into ln of this plus ln of that, right? Or if I see ln of e to the x, well, that's just x. Or if I see e to the ln of x, that's also just x. If I see ln of e, I would know that's 1. Or if I see ln of 1, I know that's 0, right? It's just another log, like any other log. All the rules apply, it's just that your base, instead of a, is now e, right? But all the rules apply. Okay. So you see ln of e, it means it's 1. Another way you can think about it, it's very convenient with the notation here. Well, let me tell you another fact, and then I will mention this. Or let me just mention it now, in general. I just want to think of what language I want to use. Okay. Rule 8 and 9 tells us a very important thing. Let me ask you guys if you can see what I meant. So when I say log to the base a and I plug into it an a to the x, I get x. And if I go the opposite, an a, and in the power I plug in log to the base a of x, I just get x. Right? Let's say I change the notation. Let's say a to the x, I call that f of x. And log to the base a of x, I call that another function, g of x. So how I can state these rules is that f of g of x is equal to x, and g of f of x is equal to x. If you have two functions that behave in this way, what can we say about the functions?
They're inverses.
They're inverses. So we never really spoke about inverse functions, but these two rules basically tell us that the log and the exponential are inverse functions. And what that means is they undo each other. They cancel each other out. Kind of like how negative is the inverse of positive, right? They cancel each other out. So when you want to solve an equation, you want to do the opposite. You can do a log to cancel an exponential and an exponential to cancel a log, right? So log to the base a of x and a to the x are inverse functions. And knowing that tells us a lot about the log. We already know a lot about a to the x, but this fact means we automatically know a lot about the log. We would know what its graph looks like, because you should know how to get the graph of a function from the graph of an inverse. And you also would know a lot of its algebraic properties as well. So one thing this means, one, they undo each other. Right? They reverse something. So if an exponential is a function that takes this to that guy, the log is going to take this guy back to the original guy, and vice versa. they'll reverse whatever the other one is doing. So if you see like a log right beside an exponential, you can almost think of them as canceling each other out and giving you the thing that works. That was here. Or if you have the exponential and there's a log right beside that, you can think of that as canceling each other out. Like they're reversing what the other guy does to the input and gives you back the original input. Right? So you can think of they cancel out. It's not really what's happening, but it's each other out. Right? So in other words, if you want to get rid of an exponential, just put it inside a log. If you want to get rid of a log, put it inside an exponential. They'll kill each other. They're inverse functions. That's one thing it means. Another thing it means is that I actually know about the graph. You remember how to get a graph of an inverse from an original function? What do you do?
Negative reciprocal.
No? Not negative reciprocal.
Solve for x. What's a good?
No, like the picture, the graph. I'm talking about the graph. If I have a function and it has an inverse, how do I find the graph of the inverse?
Switch.
You reflect in a certain line. You reflect in the line y equals x. Okay, that the inputs and the outputs are switching roles. So I know what the graph of the exponential looks like. It looks like this, y equals a to the x. Now if I take the line y equals x, I should go through the origin, and I use that as a mirror and flip it, I would get this picture. It turns out that that's the picture of log x. So knowing that these guys are inverses means I don't have to plot points to figure out what a log looks like. I can just reflect the exponential function in y equals x, and that's what a log looks like. So there's a quick way that we can get to the graph of a logarithm by understanding these guys are inverses. And in terms of solving equations and simplifying stuff, I have these rules now that I realize that, you know, if I plug in an exponential into a log, they can cancel each other, and that will simplify things. If I plug in a log into an exponential, they cancel each other, and that simplifies things. So there's and these are things, again, you have to know. Like I said, knowing the graphs of things is going to be very important eventually. So you should know that a log graph looks like that. If you didn't before, now it's one of those things you should know. It should, from now on, this should kind of, a to the x and log to the base a of x should kind of be like x squared to you. Everyone should know what x squared looks like by now without plotting points. You should be able to just draw it without thinking about it much. Now log, you should be able to just draw this without thinking about it. If I ask, what's the graph of a log? You should know, oh, it goes like that. Okay. What does it pass through here?
1.
1. Because we know that log of 1 is 0. So the transformations would also work. So what if I have change the x to a negative? What would that do? Flips it in the y-axis, like always, right? For any function, if you replace all the x's with negative x, it reflects in the y-axis. So that's what that graph would look like. And I could have y equals minus log to the base a of x. That just means you reflect this guy in the x-axis. So I'm just going to flip that upside down. That will go like this. That's what that graph would look like. Or I can have y equals minus log to the base a minus x. That flips this guy upside down. Like that. This will go through -1. This will go through. So again, all these basic rules that we spoke about functions, they apply here. Logs and exponentials, they're functions. They would behave the same way under transformation as anyone. Make a negative, it's flipping in the y-axis. All that, the x-axis. All those old rules still apply. All the laws of exponents still apply. They're still very applicable. So I just want to emphasize that. So yes, these are graphs you should memorize. At the very least, you need to memorize this one and be able to transform it into anything else pretty quickly. Let's do some examples. I want you to simplify the following. A. For this one, when I say simplify, I want you to combine it. So I gave you a long list of things, combine them into one thing. D. E raised to the power ln of x squared minus 5 ln 1. ln square root x squared minus 1 over x times x plus 1. For this one, I actually want you to expand it. So these I actually want you to do the opposite. This one I want you to contract it, combine them. This one I want you to expand it. There are different times when you will do each of these. Usually when it comes to like solving an equation, being able to go from an expanded form to a contracted form is actually easier for you. When it comes to actually doing calculus with a log, being able to go from a contracted form to an expanded form actually makes it easier for you. So you should know how to do both of these. I also want you to solve some equations for me. ln x equals 7, e to the 2x minus 7 equals 10, equal to 5, x, 2x squared plus 1. And when we finish those examples, we'll finish this section. So just copy them down and get through as many as you can. Anti-dust chalk. Such a marketing ploy. On Tuesdays, by the time I'm done teaching my class, I chalk all over. Anti-dust. Okay, let's start on this one. How do I simplify this? Ideas? Yeah.
You cancel out the ln and the e, and you're left with 5 times 2, which is 10.
And you'll be left with 10? It's incorrect. What was the problem?
But
Is it 2 to the 5th? Do you bring the 5 to the other table? Raise it to
Yes. So here's the problem. Because I know you're using that canceling rule that I mentioned before. But the important thing with rules is you have to make sure they fit the template. So the rule was here. This you can cancel them and you just have that. Or this you can cancel them and you just have that. But what's the important thing with the rule here? There is no number in front of this. You know, see that? And the fact that in the rule there's nothing there means that when you're applying the rule there can be nothing there. The fact that there's a 5 here is a problem. It means this rule does not apply. You somehow have to write it. You have to first rewrite it so that 5 isn't there. Okay? But that's a very common mistake. Sometimes students see the e's and the ln's, and again, that whole idea of, for some reason your mind just thinks if one thing is higher and the other thing is lower, it's a division going on and it cancels automatically. That's not how things work, right? These rules are very specifically constructed, right? So the fact there's a 5 here is a problem. You cannot yet apply this. They have to be right beside each other, in quotations, to be able to cancel them. If there's something in between them, you can't cancel. Okay? Same way, there's no number here. So if I have ln of like 5 times a to the x, I can't just assume that's x. It's actually not correct. Okay, so we have to do some sort of manipulation here first. Okay. So, yeah.
You bring the 5 to the power of 2, so you do 2.
Okay.
E to the ln 2/5.
Yeah. So we had a rule that says if there's if you're multiplying a log by a constant, that constant can come up in the power. Right. That was rule 3 or something like that. I don't remember what order I did them in. But yeah, there's a rule that says powers can come down and move up. You can move them like that. And now the e and the ln are right beside each other. Now you can apply that rule and think of them as technically they don't cancel, but you can sort of effectively think of it that way. And so then you end up with 2 to the 5th or 32 is the answer. There was another way to think about this. And this is using this rule. Log to the base a of b is x to the a times b. I don't know why I said log, right? And so it turns out that here I have a multiplication in the power, the 5 times the ln of 2. I could actually write it in this form. So I could take this 5 and just move it outside. And I could have thought of this as e to the ln of 2, and then the 5 is on the outside, right? Because that obeys this rule, right? And so now inside the parentheses, that rule applies. The e and the ln are right beside each other, so they cancel. And then I have 2 is left inside the parentheses. And then again I get 2 to the 5. So you really have to be careful. It's one of those things where just how the world works. It's one of those things that can be frustrating to a lot of people because the kinds of people who even make mistakes like this are the kinds of people who tend to be good at math to the point where they don't have to think about it. So the thing is, when you have that kind of relationship to math, you'll see things and you'll think of another notation. Your brain will go, oh yeah, you can just cancel. No, you cannot cancel. Right? this you have to kind of slow down and think about it a little bit. Yeah,
Wait, so why can you cancel the e and the ln?
because they're inverse functions.
Okay.
Because really, it's not, like I said, you can think of it as canceling, but really what's going on is the fact that when you plug one into the other, it just gives you the original output.
Okay.
Because they're inverse functions. So you can think of one as canceling or undoing the other. Just like how a negative will cancel a positive, or a multiplication will cancel a division. Right? I mean, though, technically that's not how you want to think about it, but effectively you can do that. Okay. So, yeah. I knew that was a common mistake. That's why I did an example like that and put a little thing here. It's very important that you follow the rules exactly. Right? Your rules are the templates. You need to be able to fit something on top of the rule exactly. Right? Any little guy that's deviating from the rule, you have to do something first. You have to simplify it before you apply the rule. What was it? Log to the base 2, log to the base 2, 2. Very confusing. What do we do? Yeah?
Don't we apply the same rule or similar rule because it's
Okay. Where?
it's the same thing as a to the log a.
Yeah, this is like your A,
X.
and that's a log
So
A.
you end up with
They're
2.
right beside each other, so I can think of those as canceling. And I'd be left with 2 to the 5th. Again, 32. Yes.
Is there anything wrong with starting in the exponent and canceling out the log?
No. So if you saw this, you could have thought of that rule as being applied here. You'll still end up, they would cancel and you'd still end up with the 5 there. Yeah. So you'd still end up with the same thing. Log to the base 2 of x minus log to the base 2 of x squared plus log to the base 2 of x to the 4th. Okay, what do we do with this one? Yeah,
Okay, so since they're all log base 2, you can,
yeah, that's the first thing you need to notice, yeah.
yeah, so then it'll end up being log base 2 and then x minus x squared. X to the 4th.
Log to the base 2 of x minus x squared plus x to the 4th.
Yeah.
Is that correct? Yeah?
Isn't it log to the base 2 times x over x squared times x to the 4th?
Right, again, so that would be incorrect. Okay, be careful. And again, this is because in your head you have this whole distributive law wired in so much that you kind of think everything distributes. Logs actually don't distribute. You have to remember that the rule that when you expanded a log, there was a multiplication here, and then it became an addition, right? Right? Thinking that log of x plus y is log of x plus log of y, that's actually incorrect, right? The distributive law does not apply to logarithms, okay? So you need to remember, whenever you see an addition out here of logs, it actually contracts to a multiplication. That was rule 2 or 3 or whatever. Okay? So that would not be the case. Logs do not actually distribute. So again, it's very important to pay attention to the rules and apply them exactly as they're written. Okay? So we have 2 logs being subtracted. What does that rule say?
Division.
Division. So this would become x divided by x squared. Now we have 2 logs being added. What does that become?
Multiply plus division.
Multiplication. So this becomes log of x divided by x squared times x to the 4th. And now you can simplify this, cancel that 3 times, and so you have log to the base 2 of x cubed. And if you want, you could write this as, you could bring that 3 down. But with the instructions like combine, I would have accepted either answer, but I should recognize that. That's true.
Quick question.
Yes.
Why didn't you add first? Like,
It wouldn't matter. Yeah?
Could you also do that a different way where you brought the 2 down and you subtract, like did like log base 2 of x minus 2 log
Yes.
base 2 of
There are
x?
often more than one ways to skin a cat. It's you just need to make sure that whatever you're doing, there's a rule that says you can do it.
It's the same answer.
You would get the same answer. So let's actually do it that way. You could have. So this is when I was applying. I don't remember the number of the rules, but this is where I was applying that rule that says, oh, division becomes subtraction becomes division and addition becomes multiplication. You could also do the rule that says, hey, you can take these powers and move them down. That's also a valid rule to apply, right? You just take this. This one you can move the 2 down. This one you can move the 4 down. And now it's like you have, 1 apples minus 2 apples plus 4 apples. You still end up with 3 apples, right? So yes, that is valid. There are often many ways to do it. Just make sure whatever way you're doing, the rule that you're applying is applied when it should be applied. This method wouldn't be as easy. For example, I threw like a 3 in here. That would kind of mess it up. Then you'd have to first split this guy and then move powers down, things like that. So you have to be careful. So you can do things several ways as long as there's some rule that applies specifically to the case that you're looking. Yeah. So a string of these would contract to like 1 log in that form. So I have e to the ln of x squared minus 5 ln of y. Okay, simplify that. Yeah? Yeah?
Oh.
You.
So 5 ln y becomes ln y to the 5th.
Okay, so she decided to apply that rule where you can take powers and move them up. I think she wants to get into a position where the e and the ln's are beside each other, so she wants to get rid of that 5. That's totally fine. So let's do it that.
And then those are being subtracted, so that means it's ln x squared over y to the 5th.
Okay, so now you apply that rule where the subtraction of logs really end up being logs of a division of things. So that's x squared divided by y to the 5th.
And then the e and then the ln.
Now the e and the ln's are right beside each other. The ln is in the power of the e. You can think of those as canceling. And so this would be x squared over y to the 5th. And again, this one, there are several ways to do this one. You could have even realized that just using laws of exponent, this is e to the ln of x squared divided by e to the ln of y to the 5th. And then this cancels and that cancels. There are tons of ways you could do it. Just make sure you're applying the rules correctly. Right? So you can use different rules to get to the answer. But this is me using the fact that x to the a minus b is really x to the a divided by x to the b. You see, that's the rule I was using. So I use the laws of exponents to simplify here as the first step, whereas here she used the laws of logarithms in the power as the first step. But these are both valid laws to use. You just need to make sure you're using them correctly. At the end of the day, you should be getting here. Okay, expand this one. So this is ln of the radical of x squared minus 1 over x times x plus 1 squared.
Well, you could do ln square root x minus, or 1, yeah, and then minus ln x parentheses x minus 1 squared.
Right. And notice that this is all in the log here.
Yeah.
Okay? Then what? You do want to get as simple as possible.
Raise them to e.
You can't raise it to. Because that would change what we're simplifying.
It's division.
What's division?
You have the log of, you have ln of one thing minus ln of another, so
Right, but if I do the division, it brings me back here.
oh my gosh.
Yeah,
Okay.
I wanted to go somewhere else.
Couldn't you say that x plus 1 squared is just x squared plus 2x plus 1? Or would
Sure,
not
would
matter?
that make it simpler?
I don't know.
Yeah?
You can do ln and then in parentheses x squared minus 1 and raise that to the 1/2 power.
Mm-hmm.
And then you can bring the 2 in front of the second ln. Maybe.
Could I bring this 2 down?
Oh no.
Why not?
It's separated
It's on
by
the
the
parentheses.
Well, because of this x in front, that's why. Is there a way that I can get rid of this x in front?
Yeah.
That's a multiplication here. What does that mean? It means I can write that as ln of x plus ln of x plus 1 squared in parentheses. Because that's a multiplication. Now here, I can bring that 2 down in front. And here, I can bring this half down in front. So let's do that in the next step. So I'm going to take this half and I'm going to move it down in front. Ln of x squared minus 1 minus ln of x minus, because it's distributed, 2 comes down. And we have that. There's still a little more we can do. Does anyone see something else we could do to get even simpler functions involved? I mean, ln x is pretty simple, and ln x plus 1 is not much simpler. We don't actually have a rule to expand the positive. So of course, I'm kind of hinting that there's something that could be done. Yeah?
Factor that with the x squared minus 1.
X squared minus 1, we actually know how to factor that. That's the difference of squares. That's 1/2 ln, what does it factor to?
X plus x plus 1.
And now what? Yeah?
Cancel the x plus 1. Or no, you can't do that.
Yeah?
Like,
Yeah.
Can you, if you, for like the first part, you could add the remaining? Like 1/2 ln of x plus 1 plus 1/2
Yeah, because this is a multiplication, so there's a rule that says I can split that up into an addition.
and then you can cancel.
So this is 1/2 of ln of x plus 1 plus 1/2 of ln of x minus 1. Do we see why there's a half on both of them?
Yes.
Yeah.
Right, because there's a half here, and I think of expanding the log rule inside of parentheses, and that half has to distribute. Okay. See that this guy and this guy, they're kind of the same. So it's like I have half an apple minus 2 apples. What would I get? That's 1/2 minus 4/2. Like there's this minus 3/2. And that's the fully expanded form that's simplified. So like I said, there are 2 scenarios we'll have. Sometimes we want to be able to solve an equation that has logs in it all over the place, and it's most convenient to combine all the logs when in that situation. But we're also going to have situations where we want to do calculus on something. To apply calculus to this is going to be very difficult, but relatively speaking, applying calculus to this is going to be super easy. And you'll see that when we get to the next chapter. But yeah, that's how I would use it. Okay, let's solve some equations. So again, one moral of the story is be very careful with the rules, right? Know those 9 rules that I gave you and make sure when you're applying them, it actually applies. That you can fill in things like a template into those rules. They're kind of what tell you what you can do from what you can't. So we're going to solve, I think, first one was ln of x equals 7. How would I solve for x? Yeah?
You have, well, you have a base of e, so you could write, I would write e to the 7th equals x.
Yeah, exactly. Another way you can think of it is something someone suggested earlier that we couldn't really do earlier, but here we can do because there's an equation. So there are some times when you want to simplify something. So you could say right away, this means that e to the 7 equals x. And this is by rule 1, the definition. Right? But there's another way that students can solve this that often is conceptually easier to see it that way, is using this canceling rule. So it's like if you have a log and you want to get inside the log, you can remember that you can cancel a log with an exponential. So if you're given this guy, what you can do is you can plug both of these into the power of an exponential. It's an equation, so you do it to both, whatever you do to one side, you do to the other side. And then you can think of this as canceling. And that leaves you with e to the 7. 2 slightly different ways of doing the same thing. Statistically speaking, over the years I've had many students, and students tend to prefer this way for whatever reason, but it's totally fine to use rule 1 in situations like this. But a lot of students just see, oh, there's an ln, put an exponential there. Or, oh, there's an exponential, put an ln there. That's a lot of students think of it that way. And it's totally fine to think of it that way. E to the 2x minus 7 equals 10. Right, so here's the e. You want to get rid of the e so you can get to the power where that's where your x is living. But we know that ln's cancel e's because they're inverse functions. So what I can do is I can think of as plugging both sides into an ln. And on this side, that cancels. So this just becomes 2x minus 7 equals ln of 10. And so now I'm just solving for x. Add 7 to both sides. And then divide both sides by 2. Do not add the 10 and the 7, right? This 10 is inside of a log, right? It's not out in the open. So a lot of times, students often skip this step, and it's okay for you to do that. I'm just saying, if you're not sure if you can do something like that. So if you're writing this down on paper and I ask you on a test or a quiz, solve this equation. I'll often see students just write faintly here that I'm ln in both sides, and then they immediately jump to this one. And it's fine to do it. As long as I can see that you're thinking about it correctly, that you're taking the ln of both sides. And then you can finish. Three equals 5 times e to the 3x. Solve for x.
Can we divide both sides by 5 and then take the ln?
Okay, so seeing that E, a knee-jerk reaction of a lot of students who do this might be to say ln both sides, but the thing is there's a 5 in front. You have to remember that doesn't fit exactly with your rule. You need the ln to be right beside the E, so the 5 in front is a problem. First get rid of it. 3 divided by 5 is equal to e to the 3x. Then at this point you can ln both sides. This side, that cancels, this gives you the 3x. And this side, you just have ln of 3 over 5. So that means your x would be ln of 3 over 5 over 3. And do not divide the 3 into the 3 over 5. Because the 3 over 5 here is stuck inside an ln. You can't move things inside and outside. It's kind of like sin x that way. Yes?
Why couldn't you put the 5 back to the 3x?
What do you mean? Put it where?
Well, like, the 5 in front of the e, like, could you put it back to 3x, so it's like 3x times 5?
3x times 5? Why couldn't I do that? Why couldn't I move the 5?
It's an e, not a log.
Because it's not a log. The rule that says you can move powers is a log rule. Right? If you have a number here in front of a log, you can move that up. There is no such rules for exponentials. Go over I actually went through the exponential rules. So go through the exponential rules. There's no rule that says you can take a number from in front of an exponential and move it up here. You can only do that with logs. So yeah, that wouldn't be the thing to do. T to the x squared plus 1 equals 1. That's D. Okay, how would you solve this one?
Base 2 on both sides.
Right, the base here is 2, so use a log to the base 2 of both sides. That would cancel this, so on this side I'll have x squared plus 1, on that side I have log to the base 2 of 5. So then my x squared would be equal to log to the base 2 of 5 minus 1. Notice that these guys are separate. And so my x would be plus or minus the square root of log to the base 2 of 5. Notice that log to the base 2 of 5 is bigger than, it's actually going to be bigger than 2, right? So taking the square root of this number is actually defined. It's not negative, right? That would be something that you should worry about. But in this case, it's fine. So that would be a little if you're insistent on working in ln, you could have done ln both sides, but your answer would look slightly different, but it would be the same when you use the chamber case model. We'll stop there. That actually covers all the topics we'll use for the first test.
Is it test Tuesday or Friday?
It's the 13th.
It's the 13th. I announced that last week.
Next week after.
So we have a quiz on Tuesday on everything we did this week, and do this homework, and you can actually start going over stuff for this test. I'll post a review to help you with that as well.
Remember any of this?
I remember it on this, but like I gotta go over it. But I could like, I could go over it.